Right, so as mentioned, I'm Marco. I work for Skyscanner. I've been a Skyscanner about almost 2 years now. So this evening I'm going to present a project that I worked on last year, about 7-8 months ago, which is essentially using reinforcement learning and more specifically multi-arm Bandit to rank the widgets in our website, well, in certain parts of our websites. So because of course Bandits are a category of reinforcement learning algorithms, I thought I'd start off with a simple introduction to reinforcement learning. I guess many of you know about this. Possibly most of you know more than I do about this. But it'll be good to just revise for a second what reinforcement learning is and just give a bit of a context before we drill into the project. So yeah, let's start with a very simple definition. So what is reinforcement learning? So reinforcement learning is, of course, a category of machine learning algorithms that essentially teaches a computer to learn from experience. I always find it easier to also explain this by explaining what reinforcement learning is not and the differences with the other families of machine learning. So there is no label data, so the algorithm will not know what the right answer is, and that's the main difference between reinforcement learning and supervised learning, of course. And at the same time, we're not trying to find some hidden meaning in the data or hidden partners or segments as unsupervised learning would do. What instead we want to do is we have a goal, a specific metric in mind or an objective, and we want to teach a machine how to achieve that objective as well as possible. So again, you've probably seen some versions of this graph. I picked this one because it's a bit more interesting, a bit more funny. So just to go through very quickly the main element of reinforcement learning. So reinforcement learning is based in two main parts. So you have an agent and you have an environment. So the agent is your computer, your algorithms. If you put reinforcement learning in the context of people, everyone is the agent. We make choices, we learn from experience, so that's what the agent is. The other component is the environment. In this particular example, I guess you probably recognize it's Super Mario. And so the goal of reinforcement learning is to take action, see how these actions impact the environment, and then essentially gather information about it, which in this case we call a reward, to put it in a more kind of formal way. And essentially you learn from that. So in the case of Super Mario, you can see from this example, the computer starts playing, goes right, and the new state is essentially the Super Mario game screen, a few pixels to the right. And then, you know, in this case, we're not dead, so yay, +1 reward or not being dead. And you do that over and over until you eventually maximize your function and you learn how to actually play Super Mario. The thing I really like about reinforcement learning is it's very kind of intuitive in a way. It's very similar to how we learn as humans, and I think it makes it quite an elegant approach. So now that we quickly went through reinforcement learning, let's go a bit more into the kind of the project or the context of the project. So let's start talking about the Bandit Problem. So the Bandit Problem generated from the world of gambling. So the intuition behind it was, well, the very first intuition was, let's imagine you are in a casino and you have a lot of slots machine that you could play. Now, of course, each of these machines will have a certain payoff or a certain reward, a certain percentage of times. And it would be great if we knew beforehand which that one is. We would be very all rich. But unfortunately, of course, we don't know that beforehand. So this is where the Bandit problem generated. So you have a sort of options, and you don't know what the payout for these options will be. And so how do you go about that problem? So in the Bandit case, the question you wanna answer, is what's the best strategy to maximize your reward after a certain amount of steps? So you wanna play your machine a certain amount of times, and then of course you want to play in the machine or the combination of machines that will let you leave the casino with the most amount of money. So given this objective, what you would do from a rational point of view if you had a very large amount of money you could spend on this. So the first thing you would do, you probably will learn about each machine as much as possible by playing each of them as many times as you can. And in the Bandit world, or in reinforcement learning world in general, this is called the exploration phase. So you just try stuff out and you collect information about your state and your environment. So you start to evaluating the effect your actions have on your environment. And then once you have enough data, you are better able to make an informed decision about the options that you have available. And here we are in the exploit phase. So once you gather as many information as you can, you just optimize your reward by possibly doing the most rewarding action all over again. Now, there is a evolution, I would say, of multi-arm bandits, which makes it very, very powerful, which is the contextual multi-arm bandit. So I'll go into the element of contextual multi-arm bandit. So in multi-arm bandit, non-contextual, you will only have the 3 bottom essential elements. So you will still have arms, which are the options that are available to you. Back to the example of the casinos or the machines. Each of the machines is your arm, and actually that's where the name arm came from, because of the slot machine example, and you pull the arm. Then of course you have an algorithm, which can be one of many. There are many, many, many variants of Bandit algorithms, and we'll go to that in a moment. And then very important is to choose your reward. So of course you need to know what you want to maximize for when you launch your algorithm. You need to know what is a good outcome and what is a bad outcome. Now, in addition to that, the contextual multi-arm bandit is really powerful because it allows you not only to learn the best decision in general, but to learn what the best decision is for each of your contexts or for each of your situation. So you're in a casino with 3 floors, you just don't learn which is the best machine in general in the casino, you learn which is the best machine on each floor, which makes it even better for carrying over your task, especially when you have many options and many different situations you want to apply your options in. So let's have a quick look at a few of the simplest, to be honest, Bandit algorithms. So the first one is called Epsilon first. This is just pseudocode, so if you're trying to understand which language that is, the answer is no language. So the Epsilon first is a very simple one. You say, I want to have a certain amount of iteration on my data or on my Bandit algorithm. And then I essentially set a threshold, a number of iterations on which I purely want to explore. And then after that, I will just use that knowledge to always exploit. So as you can see, you set a range, and then you set an epsilon. So let's say you have 1,000,000 iteration, and then you say, when iteration is smaller than, I don't know, 100,000, explore, collect data, else just exploit and get the payoff that you can. So there is a couple of problems with this. So the first one, not really a problem, but so it's very similar to A/B test, as you probably guessed. It's kind of an automated way of A/B testing. Instead of setting up a given amount of time, you just set up an amount of iteration, and that's what it does. And there's no guarantee of confidence, so that's really much depend on whatever it is that you set. So you could say, just gather information on the first 100 observations and then make the decision. And of course, on 100 iteration, it's very likely that your best choice picked by the algorithm will be a poor one. Then, moving on from this, we can improve this logic a little bit. So this is called Epsilon Greedy. It's kind of an evolution from the first one that we just saw. So in this case, you set a value epsilon, but then on each iteration, you would pick a random number, and then just say, if the random number is smaller than epsilon, explore, otherwise exploit. So a very typical setting is to set an epsilon of like 10%. So 10% of the time, just try stuff out. And then the remaining 90% of the time, just maximize what it is that you want to achieve. So the advantage of this is very, very easy to implement. The algorithm is literally these few lines of codes. And a few more to store the results. But the downside is very sensitive to noise, as you probably guessed. So because you're saying, let's say, exploit 90% of the time, again, the best option that you're going to exploit could be based and potentially will be based on a very few number of observations. So again, you may be saying exploit when, in fact, you're not using the best option that you have available. Sorry. Then, last one that we are going to have a look at, which is actually the one that we ended up using in our project after a couple of iterations. So this is called UCB, which is upper confidence bound. So we picked this because of the downside of the Epsilon Greedy. But then again, this particular version of UCB, it's pretty easy to implement. So the final score, so your final reward, would be essentially defined by that function that you can see. So essentially what that does is it kind of eliminates, or at least very much mitigates, the downside of the Epsilon Greedy, which is the fact that it's really naive. By integrating that factor, you essentially say, so the best arm would be a certain one, but you need to have explored enough on all the options. So don't assume that you're making the best choice based on 10, 100 observations. It's essentially a weighting function that adds. If there is an arm that you haven't explored in a very long time and it's kind of falling behind in terms of observation, then try that out a bit more and see if you were actually making the right choice or not. So I guess, yeah, we're done with the theory part, I would say. And we can actually look at how we use it for ranking widgets. So as per good practice of every data science project, I would say, let's start with a problem definition. So essentially, why did we start looking into this? So that was about a year ago, and a lot of people were creating a lot of content in Skyscanner in the form of widgets, advertisements, useful tools to play with, to sort your flights, and to say which airline you prefer, and all sorts of things. So traditionally, how would you go about this? So you have new options, and you usually A/B test them. Which, by the way, we do at Skyscanner. We do a lot of A/B testing. It's kind of standard practice. We A/B test every choice. But then again, given that we were expecting a lot of people to producing more and more content and a lot of diversity in that content, imagine you have a screen that looks like this. So you could potentially have, you have on the left-hand side the simplest screen of the Skyscanner app once you get your results back. And then as you go more and more on the right, you can see all sorts of kind of proof of concepts being added. And as you can imagine, if all that content existed, it would be pretty tricky to decide which ones goes on top. And also to A/B test this many permutation would not be very efficient. So, of course, because A/B test is very established at Skyscanner, we did consider that. That was the first kind of go-to option. but there is a couple of reasons we went for the bandits instead for this particular problem. So the first one is, I guess, timing. So in this graph, you can see a very simple example of A/B test, let's say. So you have something running for 2 weeks. You split the traffic, so you get 50% of the views, let's say, on each of the 2 options that you have available, and then you pick the best one. Worst one goes to 0, best one goes to 100. Which again, it works fine, but there are instances where you would like to make a decision quicker and to show the best version or whatever you want to show as soon as possible. Now, this is, for example, this is a simulated UCB bandit kind of graph. And as you can see from the very first thousands iterations, you would already see a divergence. That meaning that the best option will be shown many more times than the 50% that it would have been shown in the first week. And that makes it really important, especially when you want to, I don't know, do special campaign. Let's imagine, Halloween, Christmas, all that kind of short-lived campaign. You may want to use something like this over the A/B test. Then the other reason was, again, the optimization space. So with an A/B test, you could potentially work out all the possible permutation of what you want, and you do A, B, C, D, whatever tests. You run them, you pick it. But doing that, you would get to the best global optimal solution. But what about if you want to optimize your experience by, let's say, user or, going back to the very first example, casino floor. So you can imagine a company like Skyscanner, we have so many flights. If you combine all the possible origin and destinations, you come up to about 100,000 routes that are kind of possible in the world. And I'm probably being a bit conservative here. I haven't checked the numbers lately, but it's close to that. And so contextual bandit can be very powerful here because you can set up the context and it would collect the data for each of the contexts and make the best possible decision for each of the contexts. So that's why we decided to go down the bandit route and try that out. So we decided to start easy. Of course, as you always want to do. So we have a widget which is called the Timetable Widget. What essentially does is it takes the flights in the results page and it groups them by airline. So it allows you to very quickly and nicely pick the inbound and outbound times so you can make your own combination faster. So in our very first iteration, so we started with that and say, okay, do we want to show this widget or do we not want to show this? So in this case, because we wanted to optimize for each of the searches in a way, we picked the route as a context. So each of the origin, destination, search parameters would represent a context in this particular case. The arms, as I've already mentioned, these are your options. So the 2 layouts options, so having the widgets or not having the widgets. Algorithm, we did a very quick run on the Epsilon Greedy just for kind of testing purposes, and then we actually run tests with the UCB versions. And as a reward, of course, we wanted to maximize conversions. So how many people actually found that widget useful? So were they exiting more with the widgets or without the widget? So how did we actually implement that? So I'm sorry, this is a very dense slide. I'll go through that reasonably quickly. So just a bit of architecture. So in this case, we would collect data through Kafka, so kind of a live streaming of events in terms of how the users were interacting with the platform. And then we would have a few transformation jobs that would run every so many minutes or every hour. aggregate all the data, and then the actual Bandit function would do its thing, group by all the context that you have, and then work out the reward for each of the context. And as a consequence, in your lower bit in a database, you have saved essentially for these routes, these are the rewards. Therefore, next time someone does that search, show option A or option B. And so yeah, then we had a service that could serve the predictions based on the choice made by the bandit. So how did that go? So we ran 2 experiments in the app and 1 on the web. And we had a bit of contrasting results, to be honest. So in the app, it seems to have a bit kind of more resistance in a way. It took longer time to work out which the best solution would be. He essentially had to explore a lot more. Whether on the web, conversion significantly improved on the first test, meaning that it was kind of optimizing pretty well on that. So yeah, that's essentially what we did. It's kind of still in a testing phase at the moment, so this is kind of not in production as we speak. But as we showed in the slide before, we have the whole infrastructure. So this is a specific use case, but it could actually be repurposed to essentially do anything. It's just a service. You collect the data, you run the algorithm, and you serve the next best option. So now I guess to close my talk, I want to share a couple of things that I guess usually as data scientists maybe we don't like very much, but they're very, very important in a data science project, which is kind of doing a retrospective. So what were the issues? What could have gone better? What could have we done differently, essentially? So let's go through the kind of the main challenges, which are a mixture of technical and non-technical. So the first one, as I mentioned, so the Bandit works well in real time. Maybe I didn't stress that enough. So you want to have all your up-to-date data to make the best possible choice for the next user that comes to you. But then, of course, doing streaming processes, and especially streaming machine learning, is very, very challenging. So as we were running tests on it, we went for kind of mini batches instead, which it kind of works, but it's definitely not. Is not textbook Bandit. You wouldn't want to wait minutes or up to an hour for all the data to be aggregated, computed, and the next best option to be chosen. The other thing was, so Bandits need binary outcomes. So once you clearly define your reward, you want the essentially +1 on the environment and the +1 on the reward to happen essentially at the same time. So there is one more page view on this particular screen, and then there is or there is not an exit. But because of some specific logging implementation that we had in place, there were cases where we couldn't see specifically that happening. So there were some instances where people could exit multiple times, but they wouldn't see the screen multiple times, so the widget multiple times, but they could exit multiple times. So that kind of made it a non-binary situation. We mitigated that on the batch processing, but again, just to point it out, it's not textbook Bandits. So just something to be aware of if you ever work on something like this. Yeah, definition of reward, it needs to be very, very clear. It's possibly the thing that I spend the most on. Because again, it seems trivial to choose. It's like, of course, I want more bookings, right? But then again, it's a combination of what data is available to you, latencies, maybe certain things you need to wait an hour to get back as a feedback. So it may not be, again, real time. So you may test with, a proxies of what you want, not what you actually want. So that again, that can be a challenge as well. And then again, the problem definition, I guess. Yeah, this one was again at the very beginning of the kind of the problem space. So I guess the very, very large, like the very big explosion of content that would be challenged, that would challenge themselves on the web pages, never really happened. We optimized content, we improved things, but we didn't just go and try a whole lot of context, a whole lot of different contents in the end. So, I mean, it's still a problem that we have, like ranking things. We still have a lot of widgets, a lot of functionalities, but as of now, on that particular page, we don't have 200 possible pieces of contents competing with one another. Again, we still build a service which is working, but again, the problem definition, it needs to be very, very clear. And on that happy note, I'm done.